Hello, my name is Joanne Arsenault, and I'll be presenting a webinar today entitled Waterborne UV Solutions for Next Generation Inkjet Inks. Before I get started, I would like to acknowledge my colleagues who contributed to this presentation, and they are shown here on this slide. I would first like to discuss the differences between conventional and UV inkjet inks. We see here that conventional inkjet inks are made of polymers, colorants, additives, which are dissolved in solvent or water. UV inks, on the other hand, replace the polymer with acrylated resins, use the same colorants and additives, and replace the solvent or water with monomers, and we do require a photoinitiator to do the UV curing. There are many pros and cons for conventional and UV inks, and they are shown on this slide. The pros for conventional is that they're known chemistry, so people know how to work with them. The solvent-borne inks in particular get good adhesion on plastic substrates, and the initial investment on those inkjet ink presses has already been made. UV inkjet inks are very rapid curing. They have improved quality as far as resolution and color strength. They're low in VOC, and they have better resistance properties. Conventional inkjet inks are generally slow cure speed. They have lower resolution and color, poorer resistance properties, and certainly for solvent-borne we have high VOC content. UV inkjet inks have issues with very opaque inks that may not cure that easily. And there is a migration risk for food packaging coming from the monomers that are used in these inkjet ink formulations, as well as some photoinitiator fragments. There also may be some odor associated with the monomers. So our question today is, if we replace those monomers in UV inkjet inks with water to get waterborne UV technology, do we end up with the best of both worlds? And that's the question we'll be addressing in the rest of this presentation. So our strategy for making low migration water-based UV materials, in which case we will be using UV curable polyurethane dispersions as our water-based material, is shown on this slide. We need to eliminate chemicals of concern, things like tin or bisphenol A. We need to maximize acrylates with molecular weight greater than 500 Daltons and a functionality greater than or equal to 6. This is to ensure low migration or low extractables in our final cured product. We need to control the composition for specific requirements such as resolubility. And then finally, we want to validate low migration and indirect food contact compliance. An example here is of USCOTE 2804, but if we look at the solid content only, so not the water, we see that of that solid content, 99.5% of that content is molecular weight greater than 500 Daltons and functionality greater than or equal to 6. So not likely to extract or migrate in the final cured product. This slide shows all of the products that we have developed for inkjet inks. We have 6 of them. USCOTE's 2801, 2, and 3 for standard grades, and USCOTE's 2804, 5, and 6 for our low migration grades. We look at a number of properties in our selection guide, label-free, BPA-free. Tack-free refers to tack-free after drying but before cure, so after water removal. And we see we have 2 materials that are tack-free after drying, the USCOTE 2804 and 2805. All these materials are resoluble, which is a requirement for inkjet inks. Again, we have 3 low migration grades. For as far as reactivity, we see the USCOTE 2804 is the most reactive, and we have varying degrees of flexibility in our selection. All of these materials are compatible with each other, so they can be combined to find the right properties, including the low migration resins. The main technical requirements for inkjet inks are shown here. The first one being ink stability. This is generally tested at elevated temperature over time, and you measure viscosity, pH, particle size, or coagulum. Ink filterability is important, so you want to be able to filter the inkjet ink so that it doesn't clog the inkjet head. The materials obviously need to be jettable if you're going to be making an inkjet ink, and generally this is a function of rheology and surface tension. These inks must be resoluble after dry but before cure to avoid clogging the printhead nozzles. Reactivity is important, and you need to have this reactivity with either mercury or LED lamps, depending on what the press is using. The ink must adhere to the substrates of interest, and the resistance properties of the final cured ink must match that of the requirements of the end application. On this slide, we look at the ability to filter and jet inkjet inks. To do so, we made CMYK inks. The starting point formulation for a cyan ink is shown here. And then we filtered these materials and jetted them on a Dymatics disposable piezo print head. And all of them could be filtered and jetted. So we meet the technical requirements number 2 and number 3. On this slide, we look at the stability of various inks. Again, we made CMYK inks, so 4 colors. And we looked at 3 different use coats. And then we watched the viscosity evolution over time at 50 degrees C. So here we have our initial viscosity after 2 weeks, 4 weeks, and 6 weeks at 50 degrees C. We see for the yellow inks, use code 2801 at 2 weeks showed sediment. Use code 2802 and 2804 seem to do quite well. With cyan inks, 2801 and use code 2802 did not perform very well, whereas use code 2804 again showed good stability. For magenta inks, in general, not very good stability. And for black inks, we see, again, use code 2804 performing the best. Here's just some pictures of the various inks. And I think the takeaway here is that the stability of these inkjet inks depends on the color, the use coat that you're using, as well as the formulation of the ink. This slide looks at ink resolubility, and this is after drying the ink but before UV cure. To do this, we drew down a pigmented formulation on a glass plate and dried it in the oven. And then we placed it in water for 1 minute at room temperature. We see that all of the use coats are resoluble, although that the use coat 2804 might be a little less resoluble than the others. In this slide, we look at ink reactivity. And in particular, we're looking at surface cure, tested by either carbon black, talc, or a thumb twist. We looked at, again, the CMYK inks with different use coats. We can see that the rate of cure is best for use coat 2804. In this slide, we look at ink adhesion. And this was determined on corona-treated substrates, so various plastics. And we did the 4 colors again. And we tested adhesion with a tape pull with tests of 4104 tape. You see how the inks were cured here. And in this graph, the darker the circle, the better the adhesion. If there's no circle at all, that means there is no adhesion. And you can see, again, there's differences depending on which use coat we used, what color of the ink, and what substrate we used. So a lot of variation depending on the substrate, UV-PUD, and color. So in conclusion, I'd like to say that the use of UV-PUD'S and inkjet inks offers opportunity for novel developments, including food packaging or low migration applications. Inkjet inks based on UV-PUD'S meet the basic technical requirements of inkjet inks. This new inkjet ink technology requires innovations in formulation know-how in order to fine-tune the properties of the CMYK inks. So we're depending on the formulators to assist with improving some of the properties such as stability or adhesion. And there is a broad range of UV-PUD'S designed specifically for inkjet inks, and these can be combined to obtain various properties. Thanks for watching. If you have any questions, please feel free to contact me either by phone or by email. My contact information is shown here. Again, thanks for watching.